Alright, let's take a look at this op amp circuit, and we're told we want to find V naught, or our V output here. Again, the same approach we take with any circuit configuration. We want to divide it up into components that are feasible or easier to tackle. So looks like we have 3 op amps. Here we have this first one, the second one, and the third one. And the key here is to recognize what type of operational amplifiers they are. The first one we notice, so I'm going to go ahead and highlight it. We notice there's no feedback resistance here, or our feedback resistance is a short circuit. Okay, so because our feedback resistance is a short circuit, and I'm going to write this down, the gain becomes 1. Or the other way we can think about it is it's a voltage follower or a unity gain amp. So let me put this down here. For this first circuit, I'm going to highlight this here. Okay. The feedback resistance, RF, is 0, meaning it's short circuit. Okay. Gain becomes 1, which is known as a voltage follower. Or a unity gain amplifier. So meaning our V output is going to equal our V input. So that's one thing we recognize immediately to simplify this. So what that means to us is that the output at this point here, so let me go ahead and the output at this point here is going to be the input, which is 6 millivolts. Okay, so let's go ahead and write that down. So let's just say we just give it any, let's just say V output 1, just to denote our first output stage. Okay, the first amplifier. So we're going to say V output 1 is equal to 6 millivolts. Okay, so again, now we have that resolved. So now we're left with 2 operational amplifiers. Okay, so now we need to recognize what those are. So the second operational amplifier, we'll notice, is an inverter. So let me go ahead and highlight that. So the second one is an inverter. Okay. So I'll go ahead and write this up here. Second op amp is an inverter. So if we can redraw this if you wanted to, but all we have to know is that the inverter has an input of, in this case, the input to the inverter is going to be 6 millivolts. And now what we want to do is figure out what the output is here. Okay, and I'm going to call this V output 2. So the question is, what is that? We can solve that by plugging that into the inverter equation, which is V output 2 equals the feedback resistance minus RF over R1 times V input. Okay. In this case, our V input is going to be, our V input here is going to be 6 millivolts. our R1 is going to be 10K, and our RF is going to be 30K. So let's go ahead and plug those in here. I'm going to plug it in, so we got minus 30 over 10 times 6 millivolts. Okay, solve for that. I'm going to get minus 18 millivolts. Okay, so now we've solved for the second part of the problem, which is the second stage. So I can write this at the output of the second stage as minus 18 millivolts. All right. And I mean, that makes sense because it's an inverter. It's taking 6 millivolts, and it's also an amplifier. So it's taking the 6 millivolts, it's amplifying it, taking the 6 millivolts, amplifying it to 18 millivolts. At the same time, it's inverting it, and you have the negative sign. All right. So let's look at the last op amp configuration, and we'll notice that the last op amp configuration is actually a non-inverter. Okay, so this guy here, I'm going to highlight it here, going this way to here. So I'm going to write this here, third op amp is a non-inverter. Okay, so immediately, because it's a non-inverter, we can actually write down the equation for that. Okay, and the equation for that is going to be V output. In this case, our V output is going to be our actual V output here. So the V output out here is just the V naught, what we're trying to solve for. So we're just going to say V output equals 1 plus the feedback resistance over R1 times V input. Okay. However, in our case, our V input here is going to be V output 2, which is minus 18 millivolts. Okay, minus 18 millivolts. Notice the signs are flipped here, so I just want you to notice that the plus is here, the negative here. Again, that's not the way we typically see it, but just so you know that that's what the non-inverter looks like. So we can essentially substitute these values in here. So a couple things to note. Well, let's go ahead and just plug this in, and then I'll come back and explain where we get these values from. So our V output is going to equal 1 plus feedback resistance is going to be 8 kilo ohms, and our R1 is going to be 40 kilo ohms. So 8 over 40 times our V input. Our V input is going to be minus 18 millivolts. All right, we solve for that, and we get minus 21.6 millivolts. So this is our final voltage output, our V out here. So V output is going to be minus 21.6 millivolts, and that's what we're trying to solve for. All right, so I'm going to back up a little bit and just make a couple comments here. Because we're assuming ideal op amps, I1 and I2, okay, I1 and I2, which is the currents coming in here, so the current coming in here and current coming in here, they're going to be equal to each other. At the same time, they're going to be 0. Okay, so we have 0 current going in there. V1 and V2, which is the voltage going at V positive and the V negative here, are going to also be equal to each other, because if we're assuming ideal op amps. Okay, so technically the voltage here is also going to be equal to VO2, so this would also be minus 18 millivolts, just as FYI. So because we have zero current, the voltage here is going to equal to the voltage there, and I1 is equal to I2. So because we're assuming ideal op amp. All right, so anyways, this is how you would solve this problem. Again, tackle it, look at each op amp and recognize the pattern, and divide and conquer, if you will. And it's again a cascaded circuit, so the output of this is going to go into here, and that's going to input into here, and then finally you come up with your final result, and it's going to be minus 21.6 millivolts.